Thanks for the invitation. It's my pleasure to speak to all of you about my research work, which is on the topic of conditional computation, and in particular, fine-grained conditional computation. I will introduce those concepts soon, but first things first, let's talk about motivation behind this work in general. It is a well-known fact that deep neural networks are increasing in size in recent years, and there are very good reasons for that. For example, we have a famous paper, Scaling Laws for Neural Language Models from OpenAI, that show predictably improving test loss on various tasks, predictably improving model error when you grow the model size. And this relationship actually holds over many orders of magnitude, so we can kind of expect it to continue, right? So why bigger networks are better? So there are two main reasons. First of all, more parameters and neurons means that more knowledge can be stored in the neural network, and more layers also means that more thinking time is allowed for the model. This is all well and good, but there's a problem in that bigger neural networks are slower, but they don't have to be, and not always not necessary. So we have a few methods of reducing computation. And possible approaches, two most popular approaches, I think, are model distillation, which is to take a big teacher model and train a smaller student model based on it. So in the end, we get a smaller model. And also we can prune a big model to extract only the most significant features of that model. But those methods are kind of static, I would say. Like in the end, we have a smaller model which performs only slightly worse. But I believe we can do something better, and this something is conditional computation. So what is it in general? What is it in neural networks? So for a motivating example, showing that neural networks are inefficient, we can have an image like an image of a cat, and neural network will have to detect, is there a cat on this picture, or maybe is there a dog on this picture, right? There's clearly something, but it has to detect what is it. So current neural networks are inefficient, and this inefficiently is very clear when you realize that the standard neural network will actually spend the same amount of compute on both halves of this image. And this is clearly something that can be improved. Like the left side of that image contains just a wall. Like it's clearly, there's clearly nothing happening there. So probably less time should be spent processing this left half, right? So this is motivation for conditional computation. In general, we want to be able to first skip computation of parts of inputs, like I've shown you before, and also skip computation of certain parts of the model, because some parts of the model may be not relevant for a given input. So the most popular method of conditional computation currently used is a mixture of experts. There is a lot of implementations, but first, just a very brief recap of transformer, where mixture of experts are very often used. So every token, we have every token being processed by multiple layers. Those are primarily feed-forward layer that processes each token independently, and also we have attention. In this talk, we will just focus on the feed-forward layer. There are many methods of improving attention, but we will skip over them. And now, how can we integrate mixture of experts, conditional computation, into the feed-forward layer, and therefore into the transformer? So standard approach is to just duplicate the original feed-forward layer n times, getting n experts, and they will train like kind of independently. And we also insert a router, which is also like a small trainable neural network, which will make a decision which expert is the most relevant for a given token, or a given sequence, or a given image. And with both of those methods, with both of those modules trainable, we can train it end to end. And for example, a good example of that is switch transformer. It's a very well executed implementation of mixture of experts and iteration on that idea. And this layer with a router, we just insert as a sort of a replacement for original feed-forward layer in transformer. What is important also is that this router for processing of sequences, I mean, we use transformers for processing of sequences. For each token in the sequence, we can route this particular token to a different expert. So this is standard mixture of experts. Now, we can proceed to actually my current research, which is fine-grained conditional computation. At first, only during inference. So we got a paper published at last year NeurIPS, Sparse is enough in scaling transformers. This work was mainly done at Google, when I was working at Google. And we basically improved the inference time. We basically improved the inference time of transformers significantly, although I will tell you some caveats later. So for, let's say, medium-sized model, like 800 million parameters, what is it nowadays? We can have an improvement of 2-3 times faster inference. And for bigger models, like 17 billion parameters, somewhere half between GPT-2 and GPT-3, we can have a speed up of 20 times or so. And what is important is that we can get those speedups at no cost to model quality. Sometimes models will be a bit better, sometimes they will be a bit worse than baselines, but basically quality is kept despite skipping a lot of parameters. So how did we achieve that? Again, we need to quickly recap part of the transformer architecture, which is a standard feed-forward layer. So it processes tokens independently, and every token is represented by an activation vector. This comes from a residual stream in transformer, or like originally embedding, etc. So this activation vector is then processed by a linear projection, by a dense layer into a vector, middle activation vector of a bit larger size, usually. And on this vector, we apply also a ReLU activation. It's almost always ReLU, and so we basically will zero out some of those numbers to introduce non-linearities, right? And then we use another linear projection to get our original dimensionality back. And this output of the feed-forward layer, we just add to the residual stream for each token. So this is standard feed-forward layer in transformers. How to introduce fine-grained conditional computation? So what we did is we have introduced a controller. This is an equivalent of a router, visible here in the left corner. And this controller outputs a binary mask, a bunch of zeros and ones, but mostly zeros. It's like 95–98% zeros in our experiments. And this controller output we will use to multiply. We will multiply middle activation vector by this controller output element-wise, basically introducing more zeros into this activation vector. ReLU activation function introduced some zeros, but we introduced way more. And if we analyze it, assuming that we get a controller output first before computing the rest of the layer, we can actually skip loading and using most of the parameters in neural network, because for every zero that we created through that multiplication, there is a column in the first matrix that we can skip, because the result of that column will be multiplied by 0. So the exact value doesn't matter. We can just skip computation if we know the result already. And for the second matrix, for every 0 that we had in our controller, we can skip a single row, because this row in turn will be multiplied by 0. So we also already know the result, right? This makes us this enables us to skip 95, 98% of flops in a feed-forward layer. And this comes very surprisingly at no decrease in model quality. I will talk a bit briefly about how to design a controller. First of all, it has to be significantly cheaper to compute than the original feed-forward layer, because otherwise there would be no point. So it has to be cheap to compute, so we use a low-rank bottleneck. This seems to be enough. And for activation, we use a straight-through Gumbel softmax. Basically, this makes the output a discrete binary mask like we want, but it still provides gradients to the controller. So the controller still is learnable during the training, along with the rest of the layer. So in comparison to mixture of experts, we have basically 1,000 times smaller experts, because we have an expert is just a single neuron now, instead of the whole layer. On the other hand, we choose over 50 experts at once, 32, 64, instead of just single or maybe 2 experts like it is usually done in mixture of experts. And because of that, fine-grained decisions, the decisions, the scale of a single decision, should we use that expert or not, is really small, right? Because of that, we have no model quality impact with the same model size. Sounds pretty great. What are the caveats? They are unfortunately strong, but this is also a research opportunity always. So speed up is only achieved in very, very specific situations. So first of all, it's inference only and not training. Training is around 10% slower actually, but we only have speed up during inference. It's also only during decoding and not encoding. So that essentially means only during sequence text generation and not text processing. And we also have unfortunately terrible speed on GPU or TPU. We still have some speedups, but not so much. So those are actually awful problems, right? This is unfortunate. However, what I currently do, my work at Ideas, is about lifting those limitations of fine-grained conditional computation. So, as a motivation for that, I basically think that we have verified hypothesis that skipping parameters without decreasing quality is actually possible. Mathematically, we already skip most of the parameters, and it is only a matter of finding a design which works mathematically similarly, but it also works on the current hardware. And if it works in those specific circumstances, it can be generalized. Different designs with different hardware properties should be possible. So currently I work on generalizing those gains to training and to GPU and TPU. About ideas for improvements. If we analyze the problem, we want to route those multiple tokens to multiple experts, and we need a seemingly sparse operation, but implemented very efficiently as a dense operation on GPU or TPU. And this actually sounds a lot like the original attention mechanism, which transformers are famous for, right? So, rough idea is to take a sequence of tokens or just a group of tokens and make each expert attend over them to get an input, to get this input to the expert, and after the expert computes the output, it can send this output to specific sequences. So sort of like attention. It is actually just attention-inspired mechanism because using the original attention is unfortunately infeasible for small experts, and we want to use small experts still. But it's pretty similar. There are a lot of implementation details. So experts are small groups of neurons, no longer a single neuron, but still like 30 times smaller. We have 30 times smaller experts than standard mixture of experts approaches. And experts attend to small group of tokens, not the whole sequences like you would expect from the original attention. And also we have, unfortunately, a lot of problems with discretizations and gradients. And there is actually much more. Like this is still an active area of research for me. In terms of results so far, the speed up of feed-forward layer is possible during training on a GPU. So exactly what we wanted. And we get a similar speed up to speedups that we had before, around 3 times for medium or small models and 20 times for bigger models. However, the speed up of the whole model is small because of some bottlenecks. That is not a huge problem because I also had those problems in the previous paper, and those bottlenecks can be solved. And so far, it seems to be an improvement only early during training. So current designs are very good early in the training, like they're indistinguishable from the baselines. But later they kind of suffer, mainly because of instabilities introduced by these attention, those routers, right? But as I said, it's still a work in progress, so stay tuned for more results in the future, and you can reach out to me after the conference if you're interested in collaboration on this topic or some other topics. There's a growing team at Ideas working on transformers and scaling. So this is it from me, and thanks for listening. I will welcome any questions.